Okay, so I thought this was cool. I saw this article once. I was looking up something about when students always ask, do you curve your grade? But I don't, because I'm not a fan of saying like, if everyone does poorly on something, then they all get A's, kind of thing. Or if I have a strong class, only some can get A's and some that are like right at the level where they should get an A don't, because the curve made the A only 95% or above kind of thing. So I don't curve, but here's an interesting article, Dangerous Curves. So there's this John Hopkins professor who had this policy that he made his exams based off whatever student got the highest score on an exam. So if a student got like an 80%, the highest score on the exam, then he made that amount of points 100%, and then everybody was based off of that. So his students got wise and they said, oh, for the final exam, none of them should go into the room. And if none of them take the exam, then 0% is the high score. And so that's 100%, and everybody gets 100% on the final exam. And so they all didn't quite fully trust each other, and they sat in the hallways, because if one person went in at any point and they took the exam, even if they took the exam and got like 1 point, then they would get the high score of 100 and everybody else would get 0% because they didn't take it. But they all stood firm. And then he wound up, he was pretty cool about it. The teacher, Froelich, he said, the students learned that by coming together, they can achieve something that individually they could never have done. So he gave them all 100% on the final. Yeah, so, but then he said he changed his grading policy, so it wasn't going to happen again. It's pretty interesting. The Dangerous Curve, that's the link to the article if you're interested. So today, after the intro, we'll continue with chapter 2. And again, it's good to click through these. For students with testing accommodations, if some of you might use those in our class or even in other classes. I just found out yesterday, I was going to drop off exams at the testing center, and they are only open very few hours a week. So they're actually closed on Mondays and Tuesdays. So you can't go and take an exam in the testing center on Monday or Tuesday. And Friday, Saturday, Sunday, it's just Wednesday, Thursday they're open, and they're only open 9 to 3. So let's say you were going to take an exam from me in like a Wednesday lab section, and you were thinking you were going to have your lab time 2 to 5 to take the exam. In the testing center, you can't, it closes at 3. So, but luckily we've taken exams in lab, so you can take it in lab if that has to be the case. And this would apply to your other classes too, so just letting you know. You can come use our NMR and our IR during office hours before my first lab. I've had a couple students do that. So I think right now this week, you've been just focused on the exam, but starting next week, try to get more of that going. So yeah, you come those times. And office hours, I've had more people come into office hours, but they haven't been turning in their into Canvas. There's an assignment, come to office hours for extra credit. They haven't been letting me know there. Let me know there, because I forget to go and do it. It kind of forces me to do it when I have to grade it that way. It makes it easier. So just go in there and just say, I was at your office hour this date, and then I'll give you a point. And then I made the Google slide animation. I made an announcement about it yesterday. Hopefully you saw it. And if I were you, I would do this reaction coordinate diagram GSA before the exam. I would actually click through it all, watch and try to understand it, and then try to recreate it on paper, because that's what I'm going to ask you to do on the exam. Draw it out with your hand, because then that's practicing what you actually do on the exam. And then after you do it, look back at the key and try to grade it carefully, so you can do well in that problem, because that's going to be worth a lot of points. So there's a link to it if you haven't seen it already. Also, homework B, chapter 2 has problems that will be good for practice for exam 1. The questions 1 through 6 and then 8 through 12, that's all material that's part of exam 1. So you could check those out. That seems like a lot of problems from homework B, but some of them are really simple, like what's a nucleophile, what's an electrophile. So, and actually, I haven't done the nucleophile electrophile definitions yet. I'll do them today. So I'll let you know. Those won't be on the exam. That's it, 1, the electrophile nucleophile definitions. All right, and then exam 1 this week in lab, I already told you. So I tried to write it to take about an hour and a half, but everybody has the 3-hour lab time, but you can make it 4 hours, you can come early. Or yeah, so I've said that before. And it's going to be over these outcomes. I did erroneously say it would be over outcome 8. That's an outcome we're going to cover today in lecture, and I won't put that on today and tomorrow's exam. That'll be for exam 2. So some of the main ones we've already mentioned here. I think the ones that I see people struggling with are the sigma and pi bonding diagrams and the reaction coordinate diagrams. So practice those. There's practices. There's a yesterday's office hour, we went through some sigma and pi bonding diagram examples. So if you want more examples, they're there too. And I have actually the example I did in office hour yesterday at panel 11, I think, of the Google slide. It has my answer key, so check that out. Nomenclature, spectroscopy. All right, and then solubility organic compounds. So I need to, if you're not already done through question 14 of this assignment, the question that at that point you got to start doing the wet chemistry in lab. If you're not already there, you're pretty far behind. I was hoping that would be done last week. So, and I didn't really set a firm date to like make you get it done. So a lot of you haven't. So, but I want to get you going. So I need to get you moving in lab. So I'll use my only power. Well, one of my main, maybe not my only power. I could try guilt. It's a weak power, but my main power is points. So if you're not to 14 by lab next week, which you already should be now, you can lose 5 points from the final grade on the assignment. It's like a pre-lab check. So, so do that if you haven't. Also, I'll have you take a quiz on part D of this experiment. And so you can, if you haven't done the wet chemistry, you could skip to part D and read all the intro part. It starts on page like 49, I think. Yeah. And it's this talking about how when you give an organic molecule charge, it's more water soluble. So I've got within the solubility of organic compounds document, there's a GSA that you'll go through. And what you should actually do is start on page 49 and read like the couple paragraphs before the GSA. And then when you read the GSA, it has these reactions here that you're going to be quizzed on. So it's basically an organic soluble molecule. Has a lot more organic than polar, has no charge. It's organic soluble. When you give it charge, the minus charge, it makes it a lot more water soluble. So we predict it's aqueous soluble and blah, blah, blah. And here's like kind of a summary. And so I've made up the quiz and it's key. It's here. So that'll be a quiz you'll take on Monday and Tuesday in lab. These reactions and this theory of like having charge makes you more water soluble, it's huge for us in lab. We're going to see this in like most all of our experiments for this semester and next semester. So it's good just to get it down now. That's why I give the quiz on it. All right, and then crystallization of organic compounds. I wanted to get that done already, but I thought yesterday I needed to make that GSA for the reaction coordinate diagrams. I saw people were really struggling with that. So I'm gonna get that done. I'm gonna start working on that more today and tomorrow. I'm almost done with it, but I'll announce that next week. And then after you finish the exam today and tomorrow in lab, you might finish in a couple hours and you still got an hour left of lab. I don't want you just to leave. I want you to go run some NMRs because we want to see if we can get people to those the beginning NMRs, you know, the ethyl acetate toluene and the unknown. So if you've already done the beginning ones, a few of you have the ethyl acetate and toluene, then you can do your unknown too. Get that out of the way. And one of my best teaching practices, I believe, is to have my students use the entire lab period. I'm not a fan of like a student finishing the lab experiment in 2 hours and just going home or leaving. I'm more of a fan of, okay, if you're finished with your wet chemistry or whatever in lab, then let's do exit questions. Let's work on this and that. Let's use the whole time. So, and I want you to be in that mindset that when you come to lab, you're going for the whole 3 hours and you'll get used to it. I mean, all my students do. But I don't want you to help your other students. I don't want you to leave early. So for example, the Tuesday, Thursday lab section that starts at 10:45, it goes to 1:50. But people always forget the lab periods that are 2 to 5, they go to 5:05. So like I see people like at 4:50 going, oh yeah, I've only got 10 minutes left. I'm gonna start packing up. I'm like, no, you got 15 minutes. Let's use it all. Let's get the most out of it. It'll really make a difference if you know, the last 20 minutes where you like to leave early, if you stay there and work on a little bit, it's the best place to work on things because once you get lost and you get stuck, I'm right there to help. Classmates are there to help. So let's use our full lab periods. Don't zipper your classmates. So like if there's like 15 minutes left in lab and you start putting stuff in your backpack and you do the zip sound, it has like a Pavlovian response and it makes everybody else feel like, wait, they're leaving? Oh shoot, I should leave. And it makes you feel like the lab's on fire, like you got to get out of here because you start seeing, especially if you have like 2 or 3 people zipping up their backpack, just going zip, it makes everybody get chills, like I got to get out of here, I got to leave. Why am I still here? So don't do that. zip up the last couple minutes of lab, to get it on time. I used to mess around with my biology class. Remember, I had this big biology class. I had like about 250 people in the big auditorium, and the professor was not that organized. Like, he would have these, he'd give you this big packet of PowerPoint slides printed out, you'd buy it, and then you'd have these PowerPoint slides up, and then sometimes the slide on the screen would be in your packet and sometimes it wouldn't, and he wouldn't tell you and you wouldn't know. So when you would put up a slide, I would like look at it, I'm like, oh yeah, that's a new one. I could tell you just made, it's not in our packet. But I'd start like shuffling the papers in the packet. And if you just kind of go that, you do that a little bit, and then you hear one other person sees that they hear you shuffling, like as if you found it, then they would start doing it. And then once you get like 3 or 4 people in the classroom doing this, then the whole classroom's shuffling papers. It's funny. Yeah, so homework B, yeah, I already told you about that. It's linked, it's ready to go. There's keys for things. Feel free to come to lab early to do NMR and or the experiments, the wet labs. Just put on your goggles. So today's the exam. I don't know how many people want to come. Well, actually today, you can come early to do NMR today, but no wet chem today because you're allowed to come to today early for the exam. So if you want to come at 1 p.m. instead of 2 p.m. today, the Monday, Wednesdays lab people, you can come at 1. So they'll be working on the exam. So I don't want wet chemistry out, but the NMR I'll leave open for those who want to run NMR. So actually today, if you're in a Tuesday, Thursday lab section and you want to run some NMRs, you can run it from 1 to 5 today. That's fine, but you can't like peek in there and see what the exam looks like, but you can run it, All right. Any questions? Was I sharing my screen? I wasn't, was I? Let's see. Yeah, I was not sharing my screen. So goggles, you wear goggles when you're preparing your NMR tubes, but once you got it in the NMR tube and capped, you can have your goggles off. So shoot, I didn't have that thing. But I'll tell you what, those of you who are going to be watching this later, you have the lecture, you have the link. Here, let me go. I wish I would have known earlier. So those of you who are going to watch this video later, you have this lecture outline link because I was talking through all this stuff. Okay, so check that out by going to our organic chem step by step, and then the lecture outlines right there for today. Sorry about that. Those of you watching this in the future, it's not that big a deal. I think you'll be fine. Okay, now, any other questions before I start working on the material, new material? Okay, so we left off with chapter 2, we're in the outcomes there. And I skipped the predicting acid-base strength. This is actually kind of a big topic, and I'm gonna do that shortly. But first, I'll do this smaller one. This 9 and 10. Those are pretty easy. So this material, these 3 outcomes, I won't put on the exam. Let me actually adjust this. I think I said 8, 9, 10. I won't put that on there. Let's say 11, I guess. Yeah. 7, 8, 9, 10, 11. Yep. There we go. Okay, but these are pretty easy anyways. So define an electrophile and nucleophile. And almost all of our reactions are going to be between electrophiles and nucleophiles, or we call them acids and bases. Let me actually do the acid base first. I should switch this around. Yeah, let me change this up. This should really be first. 8. I'm always changing my material, sorry. 9, and this will be 10. 10. Okay. All right, so I've already put some stuff into our Jamboard. Me and the myself and the Otter, the anonymous Otter, are over here checking this out. I like the Otter. The Otter looks cute. Look at him. Okay, so why do I say him for otters? I don't know why. I feel like I give gender to things for just random reasons. Like cats, I always think are female and dogs male, but who knows? A lot of fish actually just change, right? I think, yeah, clownfish and a lot of animals, they can be female or they can be male. And then if there's not enough females in the school or whatever, they can turn themselves into female. Pretty cool. All right, so here we go. Electrophiles and nucleophiles. I'm gonna back this up. Boom. I wanna go to this one. Bronsted acids and bases. So a Bronsted acid is defined as a proton acceptor or donor. Anybody remember? And then while I'm waiting for your response, Annalise said, is there an office hour tomorrow? Yes, there is. So Bronsted acid is a proton donor. And you spell donor, D-O-N-O-R. Yeah, actually, I'm going to ask you to answer in the text so that I can learn how to spell things. This is good. I like this. So donor's got two O's. It feels like I should have a donor. No, donor. Okay. So in a Bronsted base is a proton accept. What is it? A donor or acceptor? Acceptor. There's two C's in acceptor. Thank you for that. E-P-T-O-R. Yep. So let's look at this reaction and see what we're talking about. I'm going to draw in a red pair of electrons on this water molecule. And I'll make this bond on the phosphoric acid here. I'm going to make that bond blue. So does anybody remember, is this phosphoric acid a strong acid? Is that one of the strong acids you had to memorize? So you think phosphoric acid is a strong acid? So I'll tell you the pKa. The pKa of phosphoric acid is about 2. So does that sound like a strong acid? Phosphoric acid is not a strong acid. It's a weak acid. It's a stronger of the weak because it's not, but it's not a negative number, right? It's not like a -7 or anything. All right, so water is going to reach out a lone pair. Boom, connect there. Phosphoric acid is going to break that bond right there. And then we're going to see on the product side, this hydronium. I'll make this bond. Oh, what am I doing? Did I just mess everything up? No, it looks all right. I'm going to make this bond red to emphasize. Oh, no, why do you have to do that? Okay, let me do this. Undo. Okay, here we go. Let's see if I can do this. There we go. This is the bond that should be red. And there still needs to be another lone pair on this. And now it's got a plus charge. That's the hydronium. Oh, I guess I already have the plus charge there, huh? Just circle it. Oh. All right, and then the hydrogen phosphate over here, it still has 2 of its lone pairs, the original lone pairs, and a third blue lone pair. Huh? I don't like the way I put that negative charge right there. Oh well. I'm gonna draw in all the lone pairs because I like to draw them all in. I used to not draw them all in. And then a couple years ago, I started doing it. Students were learning more. So now I draw them all in. Okay, so who's the acid in this reaction? Is the water or the phosphoric acid the acid? This is the acid, and it's donating the proton. Because when the water reaches over, all it takes is the proton of the hydrogen atom. The hydrogen atom is made up of a proton and an electron. So it's protons, what the water gets. There's one of it, it's one electron is in this bond, and the oxygen contributes. You can think of it, they both contribute one electron in that bond. And so hydrogen, the hydrogen atom lost its electron to the oxygen. So only the proton was donated to the water. And so that's why it's an acid, it's a proton donor. The water is accepting that proton, so it's the base. Not too bad, right? Is this reaction product favored or reactant favored? Might as well check that since we're here, huh? Let's see, we have the reactant side acid here. pKa I gave you is 2. This would be the product side acid, pKa of -2. This type of question can be on the exam today and tomorrow too, so you should know all your pKa's and how to do this. So K equilibrium 10 to the product side acid pKa minus the reactant side. So this one's 10 to the -4. It's reactant favored. And that makes sense with us saying it's not a strong acid, remember? Okay. Oh, come on, buddy. There we go, move back. Now, oh no, I guess I can't do that. Now, what about the Lewis base direct, Lewis acid base definition of acids and bases? So a Lewis acid, what is it? An electron pair acceptor or donor? Lewis acid is an electron pair acceptor. Oops. It accepts electron pairs. So does that seem like a different definition than a Bronsted? Because a Bronsted is a proton donor. That's what an acid, Bronsted acid, proton donor. Lewis acid, electron pair acceptor. It's opposite, huh? Does that apply though to our reaction above? So above, this is our Bronsted acid. It's donating a proton, right? That way. But it's also accepting electrons from the oxygen of the water, right? See how they're the same? It's just your reference. If you reference the proton, your acid's a donor, but if you reference the electron pair, your acid's an acceptor. So then the electron, what's the base then of a Bronsted base? It's a donor. Because as you see above, this water molecule is donating a pair of electrons to take the proton away. So yeah, that still applies to the same thing as we saw here. This is the same as above. You can same up here. So we got that, and then that example it applies. But the next example now, this one you've got this. I don't want to do them all red. This one we got a fluoride ion here. I want to make the minus bigger and out of the way. I want to see if I can erase that. Yeah, that would be fancy. Bye-bye. Okay, there we go. I got this fluoride, and what it does is it reaches a pair of electrons out and it bonds to this boron. Boron does this because the boron at this point has no octet. It only has 2, 4, 6 electrons, so it likes to get another bond to it. Now the boron has, as a product side, 1, 2, 3, 4, 2, 4, 6. So now it has an octet. So that's kind of the driving force of this reaction. But now let's also look at how this works. We got our fluoride. It's got the red bond there. It's got its 3 extra lone pairs. There we go. And there's a minus charge on the boron now. The formal charge changed. Is the charge balanced in this reaction? Yeah, fluoride was -1, this was 0. Overall product is -1. So the fluoride is this a reaction, a Bronsted reaction? Was there any proton donation or proton accepting? There was no proton donation, no proton accepting, huh? There's just fluoride adding to the boron. So we can't, this is not a Bronsted acid-base reaction, but is it a Lewis acid-base reaction? Let's see. So the fluoride, it donated its electrons, right? Donates electrons. So what's the fluoride in terms of a Lewis definition? Is it the acid or base? So it donated electrons, so it is the Lewis, sorry. Oh my goodness, I'm missing being at a whiteboard. Lewis base. There we go. Boom, because it's donating electrons. And then the boron over here, borane, BH3, this is a electron pair acceptor. So this guy is the Lewis acid. And almost all of our reactions this semester are going to involve Bronsted acid bases, which Bronsted acid bases are also Lewis acid bases. Or there'll be Lewis acid base reactions, and the Lewis acid base reactions are they can be, you can have something that's a Lewis acid base reaction but not Bronsted, but all Bronsteds are also Lewis acid base. So if you think of it in terms of like a diagram, it's like this. You have all the Lewis definitions, and then Lewis acids and bases, and then a subset of Lewis acids and bases are the Bronsteds. So every Bronsted acid base is a Lewis acid base, but not every Lewis acid base is a Bronsted acid base. All right, and then this will apply to something we're going to talk a lot about, these electrophiles and nucleophiles. And so an electrophile is something that is electron loving. So it says electron loving. So electron, phile is loving. Like if you're a pedophile, that's not good. You love children, but in the wrong way. So phile is love, you know? So electrophile, electron loving. And what charge do electrons have? Yeah, electrons have negative charge. So electrons have negative charge. So if you're an electrophile, you love electrons. What charge do you love? Negative. Yeah. So electrophiles love things that are negative. So if that's the case, if they love things that are negative, what charge do you think an electrophile usually has? It has. It loves negative, so what's its charge? Positive. All right, it's terrible. Positive. So electrophiles, they love negative because they're positive, opposites attract. Okay, and now a nucleus is nucleus loving. It loves the nucleus of atoms. So in a nucleus, what particles do we have in a nucleus? Do we have electrons in there? What do we got in there? We have protons. No rookie tons, these are pros, real pros. Protons, and what else? Neutrons with no charge, right? N-E, yeah, neutrons. How do I spell neutrons? N-U-E. Just seems wrong today. All right, neutrons. So the protons are positive, neutrons have no charge. So if you're a nucleophile, you love what what charge is the nucleus overall? Actually, that's the first question. What charge is the nucleus of an atom? It's got positive protons and neutral neutrons. It's positive charge, huh? And what charge then do nucleophiles love? They love positive charge. And what charge is a nucleophile? What do you think? What charge? What's its charge? Negative. Yep, because it loves positive because opposites attracts. Okay, so down below I've got a nucleophile and an electrophile. What do you think this one is here? This is a that's called a sulfide. This sulfide, what do you think is it an electrophile or a nucleophile? Annalise says, wait, the ones that say what charge do they have, aren't they off? What electrons shouldn't they have? Positive charge? I'm not sure of your question, Annalise, but let's keep going. So I'll review real quick. So electrophiles love electrons. They love negative charge, so they themselves are positive. Nucleophiles love nucleuses, which are positive. They love positive, so they themselves are negative. Okay, so what do you think this sulfide is? Is it a nucleophile? So do you think this sulfide, is it a nucleophile or an electrophile? Yes, this is a nucleophile. It's a nucleophile because nucleophiles have negative charge and they're attracted to positive charge. This negative charge makes you think, oh, it's a nucleophile. And now what about this bromide over here? This one's not so obvious. Does it look like an electrophile or a nucleophile? So you could say by process of elimination, it's an electrophile, because you're like, oh, he gave us a nucleophile. Would he give us two nucleophiles? I don't think so. And also it doesn't have a delta negative anywhere obvious right now, but there is actually a delta negative on the bromide and a delta positive on the oxygen because the bromide's more electronegative than carbon. And it's this delta positive that makes this molecule. It's this is where it reacts. At the delta positive carbon. So if that's the case, it's a electrophile. Wow. Yeah, this guy's an electrophile. I know there's a delta minus here at the bromine, and then so you could say, oh, it's a nucleophile here and it's an electrophile here, but it reacts as an electrophile. And we're going to see these a lot. They'll become more obvious. Nucleophiles are usually negatively charged, and so they're easier to figure out. Here, I'll just make up a couple more real quick. What do you think of these guys? Cyanide. The iodide here. Methoxide. Bromomethane. So what's your guess on the first one here? Cyanide, what does that look like? An electrophile or nucleophile? It's got a negative charge, so it's going to be attracted to positive things. Nucleophiles, it's going to be a negative charge, attracted to positive things. So it's going to be attracted to the nucleus of atoms, which are positive. So this one here is a nucleophile. Nucleophile. What about this next one? It's not super obvious. Iodide's a little more electronegative than carbon, so there will be a plus charge on the carbon. So does that look like an electrophile or a nucleophile? That's going to be an electrophile. This one here, what's it look like? It's got a negative charge, likes positives, it's a nucleophile. Finally, down here, we've got another delta minus, delta plus. This is an electrophile. And you'll see most of our electrophiles are going to be carbons, sp3 carbons with halogens like iodide, bromide. Okay. So, and then on exam 1, I won't ask you to identify electrophiles and nucleophiles. This will be exam 2 stuff. Okay, so Bronsted acid bases, we got it. We got electrophiles, nucleophiles. And then now we're going to predict acid and base strength based on atomic size, resonance, and electronegativity. This is going to be a good one. Okay. So we've learned pKa's, right? We've talked about it. We've said things like, if I asked you, what's the stronger acid between, say, this molecule and the similar version of it, the alcohol? Which of these is a stronger acid? Good, I'm seeing some pKa's. So we've memorized the pKa's. pKa equals 5 for this, about 5 for the carboxylic acid. pKa for an alcohol, about 16. So we know that, so we know this is the stronger acid. So good, we got that. But now what about if we have a molecule that's not one of the ones we've memorized the pKa of? How can we maybe predict which is a stronger one there? That's when we're going to look to, we're going to use the concept of atomic size, resonance, and electronegativity. So let me give you an example first of like atomic size. And also, before I do it, we're going to look mainly at the conjugate base. So here. So let's say this is the pKa memorization method. Now for this. So to do that, what we're going to do is we're going to first understand that acids and bases are in equilibrium. So they're in equilibrium with each other. And the acid can be like this carboxylic acid. It can get deprotonated and become its conjugate base. Let me actually put the conjugate in there. Acids and their conjugate bases are in equilibrium. So when the carboxylic acid gets deprotonated, it becomes an acetate. And then the acetate can go back and forth, right? So if you know something about the conjugate base, it can help you predict the acid. So if you understand that the conjugate base is energy, like if you have an acid and you look at the conjugate base of it, you say, oh, that's a really stable, low energy conjugate base. That means the acid it came from was a strong acid. So this is the technique we'll use. We'll do this. First we'll say, draw the conjugate base. And then 2, if conjugate base, sorry, is low in energy, it's stable, that means the acid is strong. That suggests, or at least stronger than something else. If the conjugate base is high in energy, then the acid is weak. Okay, so I should have typed that out, huh? I don't know, I went to pen that one out. Wait, did I move that? It's weird. Okay, so we're gonna learn ways to evaluate whether the conjugate base is high or low in energy, and we're gonna do it with atomic size, resonance, and electronegativity. So let's learn how to do that next. So we'll start by evaluating conjugate base for electronegativity. I'm going to show you 2 molecules, and we're going to predict which one is the stronger acid. So we'll start off with just, we'll go ethanol. Actually, I'm going to color code it. And thioethanol. Ethane thiol, yeah. So, oops, I didn't color code that. So if I asked you right now, before we talked about this, which one's the stronger acid? You'd be like, I don't know. I know the pKa of this is 16-ish, but I don't know the pKa of that, so I can't just tell you which one's stronger based on pKa's. But even without pKa's, we can look at the conjugate base and try to figure out which one's stronger. I'll show you how. So almost all of our reactions are relative to water as the solvent and the base. So we're going to use water. That's the most common reference in these. You could use other solvents in like DMSO, or we'll talk about that later. Other solvents that will be the base as well, but water is the most common. So here we go. We're going to deprotonate this because we're looking to see how acidic it is. So it's got to be the acid. And you see now how, like, we did the pKa quiz before, and that material is not going away. We'll just keep using it, right? If you didn't do good on the pKa quiz, you'll kind of look back at it later and go, oh man, it's so easy now. All right, we got that. So I'm going to compare this reaction to the same one, but with ethane thiol. There we go. Oh, I need a blue pair of electrons on file there. Okay. Okay, so we got this. So what we're going to do is we're going to ask ourselves, which conjugate base appears lower in energy? So, and the conjugate bases are, of course, this guy and that guy. So who seems lower in energy? Well, we'll focus on the negative charge, because the negative charge is a site of instability. Is that how you spell instability? I think so. So what the question is, the way I like to word the question is, which conjugate base can handle the negative charge better? So who do you think can handle the negative charge better, the oxygen or the sulfur? And this one's a bit complicated. I see some of you typing in the chat about it. There's two competing things here. One thing, the oxygen is more electronegative than sulfur. There's that. But there's also the fact that sulfur is a bigger atom than oxygen. So oxygen being more electronegative suggests it can handle the negative charge better. But sulfur being bigger means that that negative charge is spread over a bigger area. And that would help to stabilize it too. If you can spread out the negative charge, make it less concentrated, that really helps stabilize it. Let me type that up. I have to go small here. Let's go small. You're killing me, smalls. Let's go all, okay. Oxygen being more electronegative suggests it can handle negative charge better, be more stable. But sulfur a larger atom, so the negative charge gets spread over a larger area and is more stable. So I've got two kind of guesses at this. And which one do you think's more important? Is it the oxygen's electronegativity or is it the sulfur's size? And so what it comes down to is this is straight science. This is what science is all about. You come up with some ideas about something and you make guesses. You have two guesses here. And then how do you find the answer to the guesses? You run experiments. You go into your lab and you do a titration curve, figure out the pKa of it, right? pKa is the pH at the midpoint, something like that. Oh, do you remember the titrations back in the day? So you'd run your titration, you'd figure out, oh, it looks like the sulfur is this one's a stronger acid. And then since this is the stronger acid, now you say, oh, it looks like size is more important than electronegativity. Yeah, titration to death. I taught Chem 5 once, and I don't know if I'd want to do it again, but I did once, and it was, yeah, a lot of titrations. I tried to get rid of a lot. I tried to not do as many titrations. I think there's less now than there used to be. So anyway, so it turns out size is more important. Let me go to the next panel now. Come on. Yep, size beats out electronegativity, and this means that the sulfur can handle the negative charge better. What the heck? Come on, let me do this. And is lower in energy, more stable. And let me just show you real quick a couple things. Let's look up electronegativity and also size. Here we go. In terms of electronegativity, oxygen is right below sulfur on the periodic table. I mean, sulfur is right below oxygen on the periodic table. So you can see the oxygen is more electronegative, sulfur is less electronegative. But now when we talk about atomic size, on the periodic table, the sulfur is much larger. Atomic radii. Let's see. What's with this table not giving these ones? I like the relative size, but I want to see atomic radii on here. There we go. That's what we want. All right, here we go. So oxygen, sulfur. Sulfur is much bigger, 103, 73. I think these are angstroms. Or no, picometers, sorry, picometers. So yep, we got picometer is 10 to the minus 12th of a meter. So there's 10 with 12 zeros of picometers make 1 meter. So that, yeah, so the sulfur is larger, but the oxygen is more electronegative. Turns out the size wins out, and I like to visualize it this way. The think of the oxygen as like a baseball and the sulfur as a beach ball or basketball. So if the oxygen is here and it's got an atomic radii this big, whatever, and then sulfur is right here with much, oh, you know what? I didn't want to do it that way. I don't know why I started drawing that. Let's say the oxygen and the sulfur. The oxygen's about the size of a baseball. Got a baseball. And the sulfur is the size of a beach ball. It's It's much bigger. Got to make it colorful too. Beach ball's got to have color. There we go. We got a black. We got red. Thinking red, yellow, white on a beach ball, huh? Yeah, there's blue in there too, probably, huh? There we go. So, oh, I shouldn't have went with red, but that's okay. I want my electron to be red, but I'll make it fuzzy. That's what I'll do. Okay. So the oxygen's got a -1 charge. It's going to have a lot of negative charge concentrated on. It's going to have the same amount of just one negative charge, but it's more concentrated. Whereas the sulfur, that negative charge is spread out really thin because the bigger surface area. So they're both talking about oxygen -1, sulfur -1. So the sulfur can spread out that negative charge more and it can be lower in energy. Okay. Okay, got it. So what does that mean then about the conjugate acids? My original question, I know I've gone a long ways, was which is the stronger acid, the ethanol or the thiol? So since the CH3CH2S minus is lower in energy, its conjugate, or its acid, I should just use conjugate for this, it's confusing. Its acid is stronger. You can think of it as once the acid becomes the sulfide, then the sulfide's low in energy. It doesn't want to go back to being the acid as much. So let's look it up. We already know the pK of ethanol. What's the pK of a sulfide? pKa of thiols. Mastering chemistry. This guy's pretty good. Do you guys like him? Oh, there we go. Oh, he's got the exact same example. He's going 16 for alcohols like us. And does this confirm our prediction? We said we predicted the thiol is going to be the stronger acid. Yes, lower pKa, stronger acid. There we go. Not too bad, right? Why don't we stay on atomic size? Let's do another one. Which do you think is the stronger acid? Let's say use the conjugate base to predict which is the stronger acid. Oh, come on, baby. Come on. Let's work, iPad. Let's go. So what do you think is the stronger acid? The hydrofluoric acid? Or hydrobromic acid? No, I'll say I could say Yeah, let's do that. This is good because we don't know either of these pKs by heart yet. So what do you think? Who's the stronger acid? I'll give you some values here. We've got some atomic size, picometers. All right, and then I love Wikipedia. I should donate to them. I'm just a user. I just keep using it. Maybe I'm a teacher. I give back as a teacher, right? That's how I give back. This is electronegativity. So let's see. The fluoride is much more electronegative than bromide, but the bromide's bigger. 114 picometer atomic radii. It's over. No, it's not double, but it's much bigger still. So what's our guess? Who do you think's the stronger acid? I've looked at Khan Academy a little bit, not much, but when I looked at it, I was like, oh man, I looked at a little account. I'm like, that's not bad, doing pretty good. But I feel like whenever I look at anybody's material for more than like 5 minutes, I'm like, oh, I don't like the way they're explaining that. That's why I like to make my own stuff. It's strong. Yep. So what's the stronger acid? HBr is the stronger acid. Because its conjugate base, even though it's less electronegative, the conjugate base is lower in energy because it's so much bigger. And spread out the negative charge more. Lower in energy. And spread out the negative charge more because it's bigger. Okay. And I'll draw that conjugate base. So what I'm talking about is my bromide would look like this, the conjugate base. Has a negative charge, and the fluorides looking like this. So imagine the fluoride's a baseball, the bromide's a beach ball, and that negative charge is spread out thick on the fluoride, so it's real dense and more reactive because it's hotter, you know. Whereas the bromide, the negative charge spread out really thin, not so reactive. Would a larger electron cloud shield it from electronegative atoms? I don't know how to answer that, Santos. I'm sorry. If you're talking NMR, if you have a negative charge, you are shielded more than the NMR. But okay, so let's actually take a break now, and we'll continue with this, and we'll look at electronegativity and resonance. So far, we've just talked about looking at the size of the conjugate base, but we'll also consider, well, we considered electronegativity a little bit, but we found size would win out. And then we'll look at resonance as well.
All right, so Let me show you this trend. A big part of what we're doing is electronegativity and size of atoms. So let's look at this periodic tables, periodic table trends. I showed you this a little bit before. I think at one point I did. But now I'll show you more. This guy here, let me share it in this slide. Copy link. So I don't know how to do a pretty link, but yeah, here it is for later if you wanted to copy and paste it. All right, so what am I doing? Present. So when you look at the periodic table, we mainly just look over here for organic chemistry. In terms of size, atoms get smaller to the left because they have less protons and less electrons. Makes sense, they get smaller that way. And they get larger down the periodic table. So we saw this already. We saw like oxygen was smaller than sulfur, and we saw fluorine was smaller than iodine. And do you notice how I made the arrow bigger, thicker, going down and thinner going left? What do you think I'm meaning by that? Why did I do that? Yep, atoms, their size increases greatly down and only slightly to the left. They do get bigger to the left, but not much. And sometimes they actually break the trend. Like, I think there's exceptions in the size along the, I forget which ones, but down they get like much bigger every time. So let's check it out. We'll look at numbers shortly, but now electronegativity. What about electronegativity? Do you get more or less electronegativity? Oh, let me say this. Across the periodic table, do you get more electronegativity, more electronegative going to the right or to the left? Yeah, you get more electronegative to the right. And then what about, yep, to the up or down, does it get more electronegative? Up, right? So as you go to fluorine, you become more electronegative, so up and down. So oxygen's more electronegative than sulfur. Sulfur is more electronegative than selenium down the periodic table, right? And now Bronsted bases. This is what we were just working on, huh? We're looking at the bases, the conjugate bases. And Bronsted bases are the ones that involve protons, so proton acceptors, Bronsted base. So, we looked at fluoride and bromide, we looked at an alkoxide and a sulfide. So do the bases get stronger or weaker as you go down the periodic table? As you go down, do they get stronger? So is sulfide, the big sulfide with the negative charge spread out a lot, is that a stronger base than the oxygen with the negative charge concentrated? I think a lot of you were getting mixed up here. So because you were thinking not of the base, you were thinking of the acid. Because we found out, oh, the bases are weaker, that means they have a stronger acid. So it turns out, I'll talk about the horizontal one in a second, but it turns out as you go up the periodic table, the base gets stronger. So like an alkoxide stronger than a sulfide. An amine is stronger than the phosphorus analog. Okay. Because as you go down the periodic table, the atoms get a lot bigger. See the big change in size? If you get a lot bigger, you can spread out the negative charge more and be more stable. Okay, yeah, stronger base is a weaker acid, that's right. Okay, and then along the periodic table though, as you go left, this is interesting, you get, the base gets stronger to the left. So do you notice how on the vertical, electronegativity up gets strong, more electronegative, and base strength, they correspond, right? When you go up the periodic table. But then across the periodic table, the Bronsted bases get stronger, but they get less electronegative. Kind of weird, huh? Why do you think that is? Okay, so Ryan's got, looks like a good answer. Is that because the smaller the atom going to the left and the less it can handle the negative charge? So it gets smaller. Yeah, so you're on the right track, Ryan. So as we go down let's say as we go up, let's go up the periodic table. As we go up the periodic table, a base would get more concentrated because the atoms got smaller. But also they got more, the atom gets more electronegative, so it can handle negative charge more. So you got those two factors competing. But if you can handle the negative charge more, but you have a really concentrated charge, it's going to make you a stronger base. That's what happens along here. And then when you go to the side on the periodic table, as you go this way, you can't handle the negative charge as well in terms of electronegativity because you're less electronegative, and your size doesn't really change much. So your size doesn't really matter that much along the periodic table. So electronegativity wins out. Whereas you're up and down the periodic table, size changes a lot. So then size determines whether your base strength is. All right, and then we will look later at nucleophiles. Nucleophiles are, they'll get stronger that way. Yeah, we'll talk about it, like polarization. We'll talk about that later. Bronsted acid strengths. The Bronsted acid base, you can already do that. That should be the opposite of nucleophile, huh? So if your base gets stronger up the periodic table, the conjugate acid should get weaker. And if the base gets stronger to the left, the conjugate acid should get stronger to the right, and the opposite. Okay. So let's look at more examples of this. So can't exit. Come on, let me out of here. Let me out. Oh, I'm hitting the wrong button. User error. Okay. So the key to this is, the big key of all this is size changes a lot up and down the periodic table. Changes a lot up and down a periodic table. But size changes only a little up and down a periodic table. So for in terms of base strength, when you're going up and down a periodic table, size will determine the stronger base. And comparing down a period, I say a periodic table as if there's more than one. It's weird. Size dominates because size changes a lot. Comparing bases, base strength, bases, I'll say, bases up and down a periodic table. Size dominates. Okay, then, but when you're comparing across the periodic table, is there two C's in across? Across is one. Across, God, I can't spell. Electronegativity dominates. So let's go back to that size one. Oh, did I leave the size one? I like this one. So the difference between, say, oxygen and fluorine, 72, 73, 74, 77, 80, oh, looking pretty good. Panel 8. Come on, come on. Oh, am I there? Why won't it work? Okay, there we go. The difference between these oxygen and fluorine across the periodic table is just 73 minus 72. It's 1 picometer difference and then different in size, right? But then when you look down the periodic table, oxygen to say sulfur, oops, then it's 103 minus 73. What is that? I should be able to do this in my head. 30? Yeah. Okay. So you can see it, the difference in size changes a lot down the periodic table, right? That's why size dominates down the periodic table, but then electronegativity dominates across. There's only small changes across. Okay, and I had a question maybe. Let me see, left and right.
You said on the other one that size changes only a little, the second point.
The size changes only a little. Oh, thank you. Across. Across periodic table. Okay, there we go. So with this new found information, let's look at some examples. So what do you think's a stronger acid? Where did my, oh, too many things open over here. Okay. Let's go with, okay, we'll do it. Ammonia. And phosphate. So who do you think's the stronger acid here? I'll bring up periodic table too. I'll get a part of it. Let's take a look. Wait, what did I just do? This was dumb. I didn't want to do this example. Oh well, I'll finish it. Yeah. So this is the same as the last one. This is the size, big difference in size, right? Stronger acid. Oh, I can do 3 though, huh? Stronger acid, this pH, the conjugate base, larger. Whereas this is smaller, more concentrated. So do you think this this pKa of this, is it more or less than 35? What's your guess? Less. Good. less because it's a stronger acid. This pKa we know from ammonia is 35. So that's why I had that reference. Let's look it up. $27. There we go. It's less, 27. There we go. Okay, now where would I throw methane in this? CH4. That one you can do with pKa's. I'm doing a bad example. Let me actually not do methane. Sorry, I made a mistake. Let's do the same question though with different example. What do I want to pick? Okay, I'm gonna pick along the line. Yeah, that's what I want. Oops. Hydrogen sulfide, which is super stinky. If you ever become a chemist and your advisor or your boss or whatever asks you to work with anything with a sulfur hydrogen bond to it, try to come up with an excuse not to. Because they stink really bad. This thiol functional group, it's the smell in like skunk spray and stink bombs. Nasty stuff. Even your fume hood can't save you from the smell. Okay, so which one is the stronger acid, do you think? The pH 3 is not phosphoric though. I forget, what is it called? Is it phosphine? pH 3. Phosphane, yeah, not phosphoric acid, it's just phosphane. Okay, so phosphane or hydrogen sulfide? Who's the stronger acid? Well, let me actually go ahead and draw it out again too. Let's put on a water molecule. We'll do this right. We'll add some colors. Review that. Get good at this, right? It's on the exam today and tomorrow. We should be good at this stuff. At least not these exact these acids and bases, but these kinds of mechanisms, acid-base mechanism will be on there maybe, right? So boop, boop, burp, shabam. Okay. Not red. Oh, trying to be fast and I'm making it too sloppy and it's slowing me down. There we go. Red, boom, boom. Okay. So phosphorus, is that more or less electronegative? Phosphorus is to the left. So it's more or less electronegative than sulfur. Phosphorus is less electronegative. Okay. If it's less electronegative, that suggests it can't handle the negative charge well. It's going to be a stronger, unstable base. So what about the size though? Who's larger? Is phosphorus larger or is sulfur larger? Larger, and that suggests maybe it can handle the negative charge better because it could spread it out more. It's larger, but only by a little. Not that big a difference. Let's see. We have it on the last panels. Sulfur is 103, phosphorus only 7 larger, 7 picometers, not much. So what's more important? This is more important. So this means when the phosphorus gets a negative charge, it's not happy because it's less electronegative. It's like, I don't want to deal with this. So it's more unstable, more reactive. So that means it's a stronger base. And this is a weaker base. So what's the stronger acid? Stronger acid. We can double check here. Let's look this one. We already looked this one up. Phosphane, right? I think I already did that one. What did it say? 27? Is that what it was? Yeah, that was 27. Oops. This one's pKa equals 27. So do you think the hydrogen sulfide's pKa, is it going to be higher or lower than 27? Seven lower. Yep, stronger acid, much stronger, huh? This is actually the difference between pK of 7 and 27 is 10 to the 7 times. So this is 10 to the 7 times stronger. So a 1 and 7 zeros. So that's 10 million. So yeah, it's 10 million times stronger acid than that one because it's a log scale. Right. See where we're at. Oh yeah, we've done good today, haven't we? Ooh, we kind of went for a little bit for a ride there, huh? So I think we'll pause here for today. And here now. So view electronegativity. And one other thing, I do have my like old PowerPoint slide notes, and I don't love these ones. That's why I just did the lecture like kind of off the top of my head just now. I think that's better. But if you wanted more examples, you can check this out. It starts off with the pKa stuff, you know, oh, let's practice this kind of thing, and then that. I did take that from there. It's got a reaction coordinate diagram, kinetics, yeah. But then here's where it goes into the predicting acid base strengths. You have a stable base, it's a weak base, unstable, reactive, strong, all this stuff. And then I got I started with resonance on this one, huh? Resonance, electronegativity. Yeah, got some nice tables there. So there's some more examples if you want to check them out. That one's a pretty good one, huh?